Hey friends, welcome. Today we will be discussing postulates of quantum mechanics. Now, any new theory which is being developed is based on several postulates, and quantum mechanics is not far away from that. Depending on the type of reference books that you are using, the number of postulates may vary. As we are discussing the chemistry part of the quantum mechanics, the reference book that I have used is a Principles of Inorganic Chemistry by PURI, SHARMA, KALIA. The same number of postulates are also available in Principles of Physical Chemistry by Puri Sharma Patania. If you refer, say, any other book like A.K. Chandra, then the number of postulates, or any other foreign authors, then number of postulates may vary depending on the books. The first postulate that we will be discussing is that the state of any quantum mechanical system, it is completely specified by the wave function psi, completely specified by wave function psi, and this wave function psi is the function of position and time. So we could write psi is r and t, where r, it represents the position. That is, if we are looking at the Cartesian coordinate system, then xyz will be the position, and psi into t. So this part, or position part, is a time independent part, and this part is the time dependent part. Now wave function, it gives, or it has all the information of the system. Now this wave function may have any value. Say, suppose when we are solving the problem for one dimension box, then in case of one dimension box, or in case of the particle moving in one dimension box, the value of wave function is a sine n pi x by L. So this is the value of a wave function, and a over here is constant, n are the numbers, pi x is the coordinate, and L is the length of the box. And this particular wave function is an unnormalized wave function. So what is normalized and what is unnormalized, that we'll be looking at the later part. And the second postulate, it says that the wave function, its first derivative, that is d psi by dt, its second derivative, that is d square psi by second derivative, that is, suppose if you are taking only x, then its second derivative, all these are continuous. So continuous, it means that the distance or the spacing is very less, so we could differentiate as well as we could integrate them. Then they are finite, that is, they have certain finite values. They may have very large value, or they may have very small value, but those values are finite, and they have a single value. Okay, so they will have a single value. So any particular single value, say 20, 30, 40, or any value may arise, but that value will be a single valued only. Okay, and also this wave function is a normalized wave function. Now, not for normalization, the condition is that minus integration to plus integration, we will have psi star into psi dx, and that is equal to 1. So when we have, or when the wave function follows this condition, then the wave function are said to be normalized wave function. Over here, psi star or star, it represents complex conjugate, and psi into psi star, this is the probability density, and the probability density, it refers to the probability of finding a particle in space, and we know that particle is present somewhere in space, so the probability is always 1. So for unnormalized wave function, will have a constant, and we need to find the value of that constant, and the when we obtain the value of a constant, then that particular wave function will be referred as a normalized wave function. So this unnormalized wave function, I will be substituting in this expression, and then I will be solving this for the condition is equal to 1, and whatever value of the constant a is obtained, then our wave function will be a normalized wave function. So for this particular wave function, we have psi is equal to, when we normalize the wave function, we get under root 2 by L. So under root 2 by L sine n pi x by L is our normalized wave function for one dimensional box. And in quantum mechanics, all the wave functions that are used are always normalized wave functions. Now the third postulate, it says that any physical quantity or any physically observable quantity, it can be represented by Hermitian operator. And what is Hermitian operator, that we have already seen in our previous lecture. So say if we have any operator a cap, and this operator a cap is said to be a Hermitian operator if it satisfies this condition, that is integration psi I star a cap psi j dx is equal to integration psi I a cap psi j star dx. When this condition is satisfied, then the operator a cap is said to be a Hermitian operator. And again, psi star over here is complex conjugate, and complex conjugate, we know that complex conjugate of say any function is same if we have say complex number, or if we have say iota, then the complex conjugate of iota will be minus iota, others are same. Okay, so over here, when this condition is being satisfied, then the operator is said to be Hermitian operator. And as I have told earlier also, that in quantum mechanics, all the operators, they are Hermitian operator as well as they are linear operator. Okay, and over here psi I and psi j are the wave functions that represents the physical state of say different quantum mechanical systems like electrons, protons, atoms and molecules. Now the fourth postulate, it is very important postulate, and this postulate, it says that the allowed values of any observable a, if we have any observable a, then the allowed value of those observable a are their eigenvalue, they are the eigenvalues, and those eigenvalues are represented by a I. And in the following or in the operator equation, so suppose if we say that a cap is our operator, and we say that psi I is the wave function of any quantum mechanical system, then the solution, if we get ai into psi I, then this whole equation is referred as eigenvalue equation. This whole equation will be referred as eigenvalue equation. Okay, this value ai is our eigenvalue. Okay, so eigen, basically it is a German word, and it refers to, I think, characteristic value. So eigenvalue, and the function that is or the wave function or the function is referred as eigen function. Okay, this function is referred as eigen function. So over here, whenever we are performing, say whenever an operator is operating, or whenever an operator is performing an operation on a wave function, then we are getting a constant, and along with that constant, we are getting back our wave function. Then that particular equation is referred as the eigenvalue equation, and the function is referred as eigen function. Okay, for example, say suppose we have an operator a cap, and this operator is d by dx, and we have any say function, and that function is suppose we have e raised to ax. Okay, so when we perform the operation, that is a cap f of x, then that will be ddx of e raised to ax, and the solution of this will be a into e raised to ax. Okay, so we are getting a constant and the function is obtained back. So this constant over here is the eigenvalue, this function is a eigenfunction, and the equation that is being formed, the whole equation will be referred as eigenvalue equation. And in quantum mechanics, and the measurement of say any measurement of any observable will yield a eigenvalue, and if the eigenvalue is not obtained in any particular system, then the postulate number 5 is being used, that is, instead of say eigenvalue we are using the average value. Okay, instead of eigenvalue we will be using the average value, or it is also known as expectation value. It is also known as expectation value, and the average value, it is represented by a, and the average value for any corresponding operator, it is given as integration minus infinity to plus infinity psi star a cap psi dx. Okay, so this will be the value, or this will be the average value for, or this expression will yield us the average value for any particular observable in quantum mechanics for a normalized wave function. Okay, this is specifically for normalized wave function, and for non-normalized wave function, for non-normalized wave function, the average value will be, this value has to be divided by the normalization factor, that is plus infinity. We will have psi star a cap psi dx, and then divided by integration minus infinity to plus infinity, we will have psi star into psi dx. So this will be for the non-normalized wave function. So if any particular function is not giving us the eigenvalue, then the average value of the wave function and the average value of the observable is being obtained. Okay, and over here a cap, it represents the observable. Say if we have position observable, then the equation will be accordingly. If we have say Hermitian operator, then, or if we say we have Hamiltonian operator, then we will have h cap. If we have say, if we want the average value of say kinetic energy operator, or say potential energy operator, then there we will have v cap, and so on. Okay, so this is our fifth postulate. Moving on to the next postulate, that is sixth postulate. Now sixth postulate, it says that in quantum mechanics, the quantum mechanical operators, the quantum mechanical operators, they corresponds to the observables that are constructed writing the classical expression in terms of variables and converting those expressions to their respective operators. So basically in quantum mechanics, the operators, basically these operators, it corresponds to the observables that are taken from classical mechanics, and those observables that are taken from classical mechanics, they are converted to the respective operators. Okay, so all the operators in quantum mechanics, they correspond to the observables in classical mechanics, and those variables, they are converted into their respective operators. For example, that we have already seen in our previous lecture, that is, if we say, if we want position, then position is represented by x, then their respective operator will be represented by x cap, and operation is done as x cap of fx. Okay, similarly if we have say linear momentum, then it is given by p cap. Linear momentum, it is given by p cap of x, and the corresponding operator will be iota h cut d by dx. That is, we will first differentiate it and then multiply the function with minus iota h cut. Okay, similarly the linear momentum and all the operators that we have seen in the second lecture or in the previous lecture, they are classified, or they are the part of the postulate number 6. Okay, then the last postulate, that is the seventh postulate, and the seventh postulate, it says that the wave function, that is psi, this is the solution of the time dependent Schrodinger wave equation, or the time dependent equation, and that time dependent equation, it is given by h cap psi, that is equal to iota h cut d psi by dt, and this is xt. So this is, or this expression is the time dependent Schrodinger wave equation, and time dependent Schrodinger wave equation, it is given by h cap, and this h cap over here, it is known, this is our Hamiltonian operator, this is our Hamiltonian operator, and similarly this is the time dependent Schrodinger wave equation, and the time independent Schrodinger wave equation, it is given by h psi is equal to E psi is the smaller form of time independent Schrodinger wave equation, and this could, we will be deriving the expression for time dependent, so time independent as well as time dependent Schrodinger wave equation in the future lecture also. So hope the postulates are clear. Just we'll revise it. So first postulate, it tells us that the wave function, it completely specifies, or it has complete information about any particular system. Then the wave function, its first derivative and second derivative, they are continuous, finite and single valued. So these are the condition also for the wave behaved wave function, and this wave function, they are normalized also. So for normalization, psi star into psi dx is equal to 1. So this is the condition for the normalization. Then the third postulate, it says that any observable a cap, or any observable, it is represented in the form of Hamiltonian operator, and all the operators that are used in quantum mechanics, they are Hermitian as well as they are linear. Then for any particular observable, we will get a constant value, and the function is obtained back. So the constant value that is obtained is referred as eigenvalue. The function is the eigen function, and the whole expression is referred as the eigenvalue equation. The fifth postulate, it says that if the equation is not following, if the equation is not following the eigenvalue equation, then we will be taking the average value or the expectation value, and it is average value is given by integration minus infinity to plus infinity psi star a cap psi dx. So this for special normalized wave function, and for non-normalized wave function, we have to divide by the normalization factor. Then the sixth postulate, it says that the quantum mechanics operate in quantum mechanics, the operators in quantum mechanics, operators, they are the observables, and they are taken from quantum classical mechanics, and this observables from the classical mechanics, they are converted into the operator. For example, position, we could write it as x cap, and it is simply multiplication with x cap into fx, and p cap x is the linear momentum. It is given by this particular term. And the last postulate, it says that for a wave function, the time dependent expression, it is or the solution of the wave function for the time dependent expression is given by h cap psi iota h cut d psi by dt. So this is the time dependent expression or the time dependent part of the Schrodinger wave equation, and the time independent is given by h cap psi is equal to E psi, and over here h cap is the Hamiltonian operator, or it's also known as the total energy operator that we have seen in the previous lecture. Hope the lecture is clear. Thank you very much.